in the last lecture we have seen the states of the processes and how we can represent a process inside a process control block inside the kernel. And we said that we can have several processes in the system, and for each process we need to have a different PCB created. Okay, so let's give a simple example from the Linux operating system. So how the process is represented, how a process is represented inside the Linux operating system. So you can actually go and download the Linux source kernel source 3 source code from the web, and if you open that kernel source 3, there you will see a file shell.h in include/linux. In that directory you will see a header file, okay, sched.h, which contains the definition of a structure which corresponds to a PCB, okay, a process control block. So that structure contains all the information that a process should maintain about that the kernel should maintain about a process that is created. So let's look to the definition of that structure. So we are just showing you some elements of that structure. It has 30-50 data members. Here only 5 of them is listed. So here in the structure we should keep the state of the process first, and we have to keep the process identifier of the process. Every process that's created is assigned an identifier. So it's actually an integer. So it has it's of type PID underscore T, but actually it's just an integer value. So this is the identifier of the process. And for each process also we maintain some scheduling information. The kernel maintains some scheduling information that helps in scheduling the processes. If there are several processes are ready in the ready queue to be scheduled, then that information helps the kernel which process to schedule next, or whether to suspend the current running process and so on. So one of those information is the time slice that shows what is the maximum length of the time that the process can run in the CPU without getting suspension. Okay, so it can be, for example, 200 milliseconds. That means it can run at most 200 milliseconds in the CPU. Then it has to be stopped, and some other process has to be given to the CPU. So then we have some other information. That is, here we have a pointer to a list of structures of type struct file struct. Okay, each such structure keeps information about an open file. As we have told earlier, a process may open several files, and for each opened file we have to maintain some information. For example, what is the file position from where we will perform our next read operation? So each open file has a file position pointer associated with itself, pointing to the next position in the file from where something can be read. Okay, then after you read some information from the file, that position pointer is advanced. Okay, the next read will continue from there, and so on. In this way you can start from the beginning of the file and read until the end of the file. Okay, so such information is maintained for every opened file in a structure, the current file position pointer. And therefore for each file we have such an information maintained, and we have a list of files that can be opened by a process, and those information is maintained somewhere in the kernel, and we have a pointer to that point in the kernel where we have a list of structures keeping information about open files for that process. Okay, and if, for example, a process does not have any files open, then that does not have to point to anywhere. Okay, it can just be null. All right, and what we can have as additional information in the PCB of a process is the address space information about that process. So when a process created, it has also an address space, a logical memory, which is used by the process for its execution. It includes its instructions, data, variables, right, and also stack and so on. Each such section of the address space or such segment of the address space has a size, has a beginning address, end address, and so on. That information about the address space of the process is also maintained in a structure called struct mmstruct. The type of that structure is struct struct in C. And we have a pointer to such a structure that's created for the process. So, and the PCB of the process just maintains or points to that structure that is keeping information about the address space of the process, okay? So this is an example of the definition of a PCB in a operating system like Linux, okay? In Windows, it can be something else. It's something else. So this is how we represent the processes. So we have seen all these in the last lecture. So we were just at this point. In a multi-programming environment, we have several processes that are sharing the CPU and resources, memory, and so on. And we have to context switch. We have to switch between those processes. CPU has to be switched, okay, between those processes. And this is called context switch. And this is overhead. So during this time, kernel code is running in the CPU and no useful task is done for the applications. Therefore, we have to minimize that context switch overhead as much as possible. Of course, the time for the context switch depends on the hardware support. How much support does the hardware gives for the system, operating system, to speed up that context switch operations. So far, we have a good understanding of how multiple processes are represented inside the system, inside the kernel, using PCBs and so on. What a process needs to run, it needs address space, PC, registers, and so on, and also open files, some resources, I/O devices. These are all required things by a process to run. And now let's look how we can create processes. Do you have any questions so far? Okay, so let's look how we can create processes. Every process that is running in the system is created actually by some other process. Only the init process may be a special process that is created at the system startup is just created by the kernel. But all other processes, user processes that you are using, okay, the word processor, Excel sheets, and so on, are created by some other process. So init process can create some other processes, and those processes can create some other processes, and so on. For example, if you are interacting with a window in Linux, okay, there you have the command shell, which allows you to type the commands, right? So that command shell is actually a process. It is allowing you to type commands, right? Then it gets the name of the command and executes that. At that point, it creates another process, the process to be executed. So now the shell process has created another process, whose name has been typed by you, that program that you want to execute. So it becomes a process created by the shell and it runs, okay? So that program that you are running is actually created by the shell process. So in this way, we have parent-child relationship among the processes. So the shell, for example, is the parent that can create a new process that is running the program whose name has been typed by you, okay? So a parent process, therefore, can create one or more child processes, which in turn can create other processes. In this way, we can form a tree of processes. So this can be, for example, a snapshot of the system and the processes that are created in the system and their relationship, okay? So here, for example, one process created this process has created that process, and so on. So we can have several processes created by the same process, okay? Each process has only one parent, okay? Sometimes parent may be changed. If this parent terminates, then the parent of that process may be that one, okay? This one can be assigned as the parent of that process. This is possible. Or sometimes in Linux, for example, if the parent of a process dies, the init process, okay, becomes the parent of that process, okay, of that child process. So in this way, we have a tree of processes in the system, and whenever a process is created, the kernel always assigns it a unique process identifier. Okay, for example, the ID of that process can be, for example, 150, and the ID of that can be 160, and so on. The thing that is ensured is that all these IDs for the process are unique, okay, but they can be recycled. The ID that is assigned to that process, if that process terminated, then it can be assigned to somebody else, okay? Usually the ID space is between 0 and 65,000, okay? So you can assign an ID to a process, and when that process terminates, that ID can be assigned to some other process. But considering all the processes that are running at the moment or started, each have a unique ID, all right, as the identifier. of the process. So when a child process is created, then there are some issues whose answer depends on the operating system. How much sharing should be done by the parent and child resources? Parent and child, for example, can share all the resources, the text, the instructions, the variables, global variables, and so on. This is possible, but the system may choose to not do that as well, okay? Or they can share only some resource. For example, the open files can be shared, but nothing else. This is possible, okay? So there are several options available, and it depends on the operating system what happens when a new process is created, okay? So you have to read the manual page of the system call that is used to create a process and see what it is doing, okay? How much sharing is happening between the parent and child and so on. So also there is execution alternatives. So if the parent and child, if the parent creates a child, what happens? Whether the child and parent can execute concurrently, or, for example, parent has to wait until the child terminates and then can continue with execution. So these are alternatives that can be enforced by different operating systems in different ways, okay? Sure.
Parent and children share all resources without share no resources.
So that means that they operate on their own resources if they are not sharing resources. For example, they operate on their own variables, on their own global variables, okay? But if they share resources like their data segments or data sections in their address space, that means they are actually acting on the same global variables. So if one process modifies the value of a global variable, then it becomes immediately visible to some other process that is sharing that segment, okay? But if there is no sharing, then if one process updates a resource, a variable and so on, then the other will not be aware of that, okay?
Hocam,
yes.
Veya prosesler concurrently çalışıyorsa birinin değiştiği variable, global variable diğer prosese nasıl etki ediyor?
If they are sharing their data segments, then it will affect. But, for example, in Unix, with the fork system call, you are not doing that. The parent and child has completely different address spaces, no sharing at all. Okay, but it is possible to allow them to share. So we are just talking about the alternatives here. Okay, so regarding the child's address space, so what does it contain? There are two alternatives here. So when the parent creates a child, okay, so child usually has its own address space, its own logical memory, you can say. So when they are stored on the RAM, they will be occupying different portions of the RAM, okay? So therefore, when variables are here modified, they will not be seen here. But what should be the content here initially when that is created? There are two alternatives for that. It can be the exact duplicate of the parent, meaning that the instructions, the global variables, the stack state, and so on will be all copied to here into a separate address space, child's address space, so that child will also execute the same set of instructions and will have the same global variables, but then those global variables will be occupying different regions in the memory, so therefore a modification here will not be seen by that, but the names of the global variables and so on, what kind of global variables you have will be the same. So this is one alternative as the address space of the child. Another alternative is the child, after getting created, can execute a completely new program. So it can have a completely new address space content, and that means a completely new memory image. So the instructions can be totally different. It can be taken, new instructions can be taken from a different executable file. The variables can be totally different and so on, okay? So there are two basic alternatives here. So one is the child has the copy of the parent's address space, and the other alternative is the child has a new program loaded into it, okay? In Unix, for example, or Linux, we have a system called fork that creates a new process, okay? And the new process will have its own address space, but it will be the exact duplicate of the parent, okay? And then after that, you can execute the exact system call to replace that content, that address space. So after child is created with the fork, okay, the address space content will be the same initially with the parents. Okay, but you can immediately change it to execute a new program. The address space can be replaced with a new memory image, with a new program, so that the child starts executing a totally different program. If you want to do that, then you have to use a system called exec. So exec is a system call that is not creating a new process, but it's just changing the address space of the process. Okay? Fork is a system call that is creating a new process, but it is not loading a new program into it. It's just creating a new process that is the duplicate of the parent initially. Okay? Of course, then they can run concurrently, and then they can modify their own global variables and so on. But initially, the state of the global variables and so on is the same. Okay? In the child and parent, and if you execute the fork system call. So now we will see a C program example about how we can create a process. In the projects, actually, you will see such examples. Okay, in the projects, you will do such examples. You will do projects that are using these system calls, fork, exec, and so on. Okay. So let's look to these C programs. That is also given in the book. So in that simple C program, what do? We first define a variable, okay, inside the main function, n. And that is of type PID type. That means n can store a process identifier. Actually, it is just an integer. It's a variable of type integer, okay? So here we will store a process identifier. The process ID of the child process will be stored here. So it's a very simple program, and that program will do what? It will just create a new child, okay, with the fork system call, and then the parent will wait until the child terminates. And the child will also call exec system call, exec LP system call to run a different program. So we will trace this program and understand what's going on when a process is created and when its memory image is replaced to execute a new program and so on. So what happens when a fork is called, what happens when exec LP system call is called, we will understand with this example. So this simple program calls the fork system call at this point. So before the fork is started, this is the system state. We have one process running in the system, let's say, okay? That process has a variable n defined, which is not initialized, so we don't know what value it has, okay? So that process has an identifier, process ID, PID. Let's say it is X. Kernel assigns that ID to the process, right? So let's assume that the kernel has assigned X as the ID of that parent. So this is the system state before the fork is executed. Assume we are running this program, okay? So when fork is executed, what happens? Fork system call is running in the CPU, and what is the job of the fork? The job of the fork is to create a new process. So let me briefly describe you what fork does in UNIX or in Linux, okay? It's a system call that you can use to create a new process that will have its own address space, but initially that address space will be the exact copy of the parent's address space. So then the fork will create such a process, and that child process can also start running in the CPU whenever the scheduler decides to run that CPU. And also fork returns a value. As you see, fork does not take any parameters as input, okay? You just call it and a new process is created. Here you don't give the name of a new program and so on, because the new process does not run any program. It runs the same program, okay? Because the same program address space is copied into the address space, into the memory of the child process. That means they have the same set of instructions here that is to be executed. So the return value of fork is this. After the fork, before the fork you have a process that will call the fork. After the fork you have still that process and a new process that's created, child, okay? The fork returns as the return value to the parent process. As the return value, it returns to the parent process the process identifier of the child. The fork is a system call, kernel code, that creates the child process, a new process created, and that process will have an identifier, a PID, right, assigned by the kernel. Assume that ID is Y. So kernel has created this child and assigned the process identifier Y to that, okay? So that Y is returned, the PID of the child is returned to the parent process. But to the child process, only 0 is returned. So when fork returns, parent gets the PID of the child, but child gets 0. So after fork return, after this statement is executed, system call is completed, then the program will continue with this statement, right? So at this point, what do you have in the system? 1 or 2 processes? 2 processes, right? One process become, up to here you had 1 process, parent. It executed fork. Now, after that point, you have 2 processes in the system. Also a child process, which is also running the same code. So parent will continue from here to run, from where the child will continue doing at the same place, okay? Child will also continue to run from this place. Child will not fork and create another child, okay? Otherwise, we will have recursive call of forks, which will immediately create lots of children process, and we will exhaust the resource of them, okay? So you just create a child which continues from this point, okay? And parent will also continue from that point. So what is this statement here? Here we have an if statement. If we would not have an if statement and so on, what would happen? The child and parent would execute the same code here, whatever they see here as the statements, assignment statements, arithmetic operations, and so on, okay? They will execute the same code. You have 2 processes in the system that are doing the same thing. This is possible, right? You can just create 2 web browsers, or you can just create 2 word processors. That's possible, right? That means your one process, for example, is creating another process that is doing the same thing. Okay? But here, with the if statement here, what we can do a little bit more. We can enforce parent and child to execute different things. Different pieces, different parts of the same program can be executed by the child and parent by the use of the ifs. Here we will see that, how we can enforce the child and parent to execute different parts of the same program. Okay, this is an example for that. So here we see that, we see a comparison. We see a condition here, okay? We compare n, which is the return value of fork, with 0. Usually every system call can sometimes fail, all right? Whenever a system call fails, it will return -1 or a value less than 0. So the first thing that you should do after calling a system call is to check the return value. If it is less than 0, then you can write a message to the screen and terminate. Because system call has failed, you cannot continue. There is nothing to be done. Most of the time you cannot recover from that. This is not an expected result, okay? Something really bad, something bad has happened in the system, so the return value is -1 and or less than 0, so you cannot do anything else, and you have to terminate. Okay, you call the exit system call and terminate. So this is the error condition check. If, however, if this is not the case, that means n is 0 or a positive value, right? So you check that. If n is equal to 0, all right, then you execute this statement. Else, that means n is greater than 0, a positive number, then you execute those. So these conditions are evaluated, and these statements are evaluated, remember, by both the parent process and the child process, okay, after the fork. After the fork, you will have parent and child process in the system, and they will execute those statements. So both will check n, assume n is 0 or greater than 0. There is no error in the fork. So they will not enter to here, both of them, right? After fork, we have 2 processes. They are sharing the CPU. One of them will be running the CPU for a while, and then another one will be running the CPU for a while. It depends on the scheduler, who will run first, and so on. You cannot make any assumption about that, okay? But after fork, you will have 2 processes running. So now, assume there was no error in the fork. Child has been successfully created. So both of these processes, whenever they are given the chance of using the CPU, will not execute those statements. So they will do this check. So parent is doing that check. If n is equal to 0, do you think that for the parent this condition will be true or false? Remember, for the parent, fork will return. Fork is a system call that can return a value, right? For example, the return value can be pushed to the stack of the parent process. And when the parent executes, it can get the value from there and assign it to this variable. So as a result, when fork is executed, the parent will have the value of y in its n variable. Y is the PID of the child, right? Because fork returns to the parent the process ID of the child, and the process of the ID of the child was y. Therefore, parent will have y as the value of n. What about the child? System call fork returns 0 to the child process as a result of fork. That means it pushes 0 into the stack of the child process, and when the child get chance of using the CPU, when it starts executing, it will pop that value and assign it to its variable. So child will have value 0 in its variable n, right? This will be the only difference between the child and parent after fork has finished executing, okay? Everything else will be the same. Their data segments, the remaining elements, their stack segments, their instructions will be everything the same. They will have complete different address spaces, but the content will be the same except those two variables, okay? So now we look to the value of that variable, okay? And so when the parent executes this piece of code, it will see that n is not equal to 0 because each process has a positive identifier, 1 or greater than 1, okay? An identifier that's 1 or greater. So a parent will see that n is not 0. Therefore, for the parent, this condition will be false. So a parent will not execute this piece of code. It will jump to here and start its execution from there. But what about the child process? When the child process starts running in the CPU, it will also do those checks, right? It will start executing from here. If n is not smaller than 0, so it will not go to here. Is n equal to 0 for the child? Yes, that condition will be true for the child, and child will start executing this piece of code here. You can have one or more statements here. With the use of such a conditional if statement, okay? And with the use of this variable, whose value is assigned the return value of the fork, you are enforcing the parent and child to execute different parts of this program. They execute the same program but different parts, okay? So that means you write a single program, no two programs for the child and parent. You write a single program and you use fork in that, and then when you execute that program, some part of the program is executed by the child process and some part is executed by the parent process. You can build the application logic of your program in this manner, okay? So let's look what happens here. So parent will continue running. So after the fork, if parent runs, it will start running, or it will continue running here, and here it makes another system called wait. So let me introduce you the wait system call. If you call that wait system call, you are enforced to wait until the child process that you have created terminates. Then you can continue. So the parent will be put by the kernel into sleeping waiting state until child runs and completely terminates. Okay? So now parent comes to here and waits. Okay? It cannot go further. If child is given the CPU, what it will do? It will start executing those instructions or those statements here. Okay? So what does it say? Here we execute another system call, execlp. All right? Let me introduce you now this system call. It's a system call that enables you to run any program in your address space. You are not creating a new process, but you are changing yourself. You were executing these statements. Now, when you do this, from this point on now, you are wiping yourself, your address space, and loading this program that is specified here as a parameter. Okay? So execlp now, this is executed by the child process. Okay? So after it is executed, that system call is called and executed. Then execlp is a system call. That kernel routine will run and will go to the disk, will take this program and load it into the address space of the child. So the previous address space of the child, which was including this, which was the exact duplicate of the parent, will be wiped out. You will lose it, okay? It will be overwritten with the address space generated from this executable file, which is an executable ls. ls in Unix is what? It is just listing the directory, right? You see with what are the current files are in your current directory, right? So now that means the child process will run that program. So that program is loaded into memory and replaces the address space of the child. And after loading it, execlp it starts running that program. So child process will start running the first instruction of this program. After that point, the child process will run this. That means this program is running now. Here, this process is running that program. What is doing what? Which is doing what? It is just listing the files currently in the directory, okay? You have in your directory. And then it terminates. Then what you can do, of course, when it terminates, kernel will know that. And kernel will also know that parent was waiting for that. Then the kernel will change the state of the parent to ready again, so that parent will be able to continue with the next statement after the wait, because the parent was waiting here. Okay, so then parent will execute this statement, which is a printf statement. Okay, so it will write to the screen, child is completed, and then it will return. Okay, so this is a simple program, 15 lines of code maybe, that is doing this task. Okay, you just write this program, and then when you execute that, it becomes a process. It creates a child process. In the child process, it runs this program, which is listing the files in your directory and then terminating. And then the program that you have started also terminates. And before terminating, it writes this string to the screen. Okay? Yes?
From child's perspective, where do you set n to 0? Because first statement does not ensure n to 0.
Right. Child starts. Right. Child also actually, this is as a result of that. Okay. You will have the kernel writing the return value of the fork. Okay. Into the variable n of the child.
Return value of the fork does not seem by the child. I think we need an n equals to 0 statement just after the first statement.
No, return value of the fork. The kernel has the right to access the address space of the child, okay? So you can touch to the address space of the child if you wish, the kernel. I am not very sure exactly how it's done, whether the kernel is pushing this value to the stack and then the child itself is getting it, or it can also directly go to the address space of the child into its stack directly and put the value there. This is also possible. You cannot touch to another process address space. A process cannot touch to the other process address space or the kernel. But kernel can touch to here and there, okay? It can access it. It is possible. Any questions? Yes, again, you can, for example, if you wish, now you can call the fork here again, whenever you want. After this point, if you say, for example, n is equal to fork again, okay? A new child will be created. Let's say its PID is z, okay? Then the new child will be another process here. And in that child will be 0 because the fork returns 0 there. But here you will modify your variable with the ID of the new child, okay? So n will be now keeping in the parent the ID of the new child. So parent will have, for example, z here, okay? But of course you can declare another variable here, define another variable m, or you can define an array of PIDs here, where the second element of the array may keep the ID of the second child, and so on, okay? So you can just assign it to a different variable if you want to keep the PIDs of all the children that you have created, okay? Otherwise you will overwrite the value.
Hocam iki tane child yarattığımız zaman o iki child'ın n değeri 0 eşit olacak değil mi?
Right, exactly.
Dolayısıyla o iki child'da o n eşittir 0
Right.
kodlarını çalışacak.
Exactly.
Dolayısıyla iki proses aynı işlemi yapacak değil mi hocam?
Right, but here, for example, you start creating the child. If you put the fork here, you start creating the child here. The second child will start executing from that point, okay? Not from this point, okay?
O zaman yeni bir
The new child will be created only at the point that you call the fork second time. So each fork creates only one child, okay? So if you call the fork again, the new child will be just start running at that fork, and yes, if you have a condition statement like that, it will start running, going into that statement and running that.
Hocam peki child process aşağıdan başlayacaksa
If you depend on where you put the fork, the second fork.
oraya koyarsak o zaman hiçbir şey çalışmaz hocam. Çünkü
Right.
aşağısı
So
yani
it-
işte sıfır
Exactly.
yapan bir kod aralığı yok orada. Kod parçası.
Here, if you want this parent to create a child, do you want this parent to create a child or that child to create a child?
Yok. İlk
Okay,
parantez
this one, right?
Bir tane farklı child.
Right. That means then, after calling and creating this one, for example, you can just call it here fork. Before waiting, you can create another child, okay? And that child will be created, and then you can put another if statement here. Okay? Yes, you have to put another if statement here so that you can specify in that if statement the portion that the child will execute and the portion that the parent will execute, and that can be the portion that the parent will execute.
Bir sorun daha hocam. Peki hocam 2 tane için çözülebilir bir mantık da bu. 15 tane fork yaratacağım child. Ondan
Right,
hepsi
right.
iç içine giren bir şey olmayacak mı?
Depends on if your application requires 15 child to be created, and for example, you can just put a for loop here as well. Inside a for loop, you can just create 15 children, okay?
Ama fork yaparsak da 15 child'da hep aynı şey yapmış olacak.
Right. Then you have to create manually. Depends on the application. You have to create, if you want to create 16 separate child, each executed different, then you have to put 16 if statements here. Okay? That's the case. But if you want to create 16 children that will do the same thing, then you can do it in the for loop. It totally depends your application logic, okay? What you want to program. Then you can place the forks and if statements accordingly in the program, okay?
Ben şey kısmını tamamladım. Şimdi parent'ten child oluşturduk, orada herhangi bir sıkıntı yok da. Ben mesela aynı child'den bir tane daha oluşturmak istersem, bir daha fork'u çağırdıktan sonra oradaki if else statement'lerin aynısını bir daha yaparım.
Right, exactly. Yes, exactly. So the code after you create a fork, after you call the fork, the code after that will be executed by child and parent. If you put F statements, then you enforce some part to be executed by child, some part to be executed by parent. Otherwise, everything will be executed by both, okay? All right, so let's make a trace of this now, okay? So we can actually trace how this is working. So how this systems call can be used, okay? So we will trace the execution of a program that uses the fork system call, okay? So basically the same program, but we will go into more details while tracing this, okay? So assume we have this program, this simple program, okay, that is started, okay? So it is loaded into memory. Assume this is your memory, main memory, RAM. So the kernel is loaded in memory as well, right? It's already loaded. So the kernel is just another executable. So it has its own text section, code segment, right? Data section. In the code segment, it has sequence of kernel instructions, system calls, and so on, all the kernel routines. And in the data section, it has its global variables, its variable structures as well, okay? Here we show it in C. Of course, the kernel memory image or the process memory image will contain object code, machine instructions, right? But since it is very difficult to show them here and understand what's going on, we are representing their meanings with C code here, okay? So we have the kernel code and process code, the program code loaded into memory. And assume this is the code of the program. And you can see what it's doing since it's in C, but it's shown in C, but actually in memory it should be object code, right? Because you have compiled the program, the compiled program executable file is an object code, machine code, you load it. So now assume this process is created by the kernel, right? You start up that process, allocate memory, kernel loaded it there and prepared a process to run. So then that means a PCB is created for that process, right? So the kernel maintains the PCB of that process. And that process has its address space, staying in the physical memory somehow. It may occupy a contiguous region, or with complex memory management techniques, it can actually be sitting in different portions of the physical memory. But no matter what it is, we have a logical memory used by the parent, but by the process that's created. So it has text, data, and stack sections. And we have seen that we have in the main function of the program a variable defined, and so it is actually sitting in the stack because main is also a function and local variables of the function are in the stack, right? So variable n is in the stack, and we have the text portion of the program having being something like that and including a statement fork, okay? So now let's assume that this process is started, is executing, and then it's at this point in its execution. All right, so that means this process was executing in the CPU, and now it is at this point in its execution. So the program counter register in the CPU is pointing to that instruction, okay, to its object code correspondence. This is C code, but actually the program counter always points to the instructions that are object code, right? Machine instructions. So assume this is the current execution point. So the PCB of that may also point to here. So what will happen now? So now the process that was running in the CPU would like to do a system call, right? It would like to execute fork system call. That means if the fork system call is here, the code of that, the object code. So we have to have a jump to here, right? So we are jumping into the kernel now. So this is a system call, software interrupt. That means the current running application is suspended, right? And here, the PCB of that application stores the PC value, all right? PC value, here in that PCB, program counter value, stores the current instruction or next instruction to be executed when that process is run again in the CPU, right? So we save that PC value that was used by the program here, okay? So then we jump into the kernel. So now kernel code is executed in the CPU. So the instructions here making the fork system call are executed in the CPU, okay? So then fork is doing what it has to do. So what is the job of the fork? To create another process, right? So what does it involve to create another process? It involves creating a PCB structure, an object that will keep information about that process, right? So it requires that new process to be assigned a process identifier. Assume the kernel assigns Y as the PID of that. So the PID field of the PCB includes Y. That means this is the identifier for the new process, okay? And then the address space for the process will be created, and it will be what? So memory for the child will be allocated, the address space of the child will be created, but the content of that address space will be what? The exact duplicate of the parent. This is the fork semantics. This is what fork is doing in Unix, okay? So therefore we have the data, text, data, and stack sections of that child to be copied, to be taken from the parent. So a memory copy is happening to here, okay? In this way, the address space of the child process is prepared, obtained, okay? So that address space contains the instructions that are the same with the parent's instructions and so on, and the current execution will take place from that point, just after the fork. So therefore, the PC value, program counter value of the new process is initialized to point to here, right? That means when that process is given the CPU, it will continue executing from here. It is not executing at the moment. Kernel code is executing to do all these tasks, right? So then what will happen? So just before fork returns, so in this way we will have all this setup done, the second process created, but just before fork turns, it is returning these. It returns two different things. It returns to the parent the PID of the child, which is Y. So a parent has that and assigns that to the variable n, okay? So as a result, the parent will have Y as its value. And the fork returns 0 to the child, which is assigned to the value n of the child. The same variable appears here also, right? But has a different storage. Two variables, here and there with the same name and so on, but they have different locations in the physical memory. Therefore, you can put Y here and you can put 0 here, okay? Then fork is done. System code running is done. So now kernel scheduler can select either this process or that process to run next in the CPU. Which one is selected, we don't know of, okay? Depends on the scheduler, and we cannot make any assumptions about it, okay? So assume parent is run again. So context switch will happen. Again, switch to parent process will happen. So parent will start running in the CPU. So for that, the CPU state is loaded from here to there. So PC value here is pointing to here. That means it's copied to here. That means this PC will now point to this instruction, right? To be executed next. So that parent will start executing in the CPU. So this instruction will execute. So it's a comparison. It will compare the value of n with 0 So the condition will be false, right? Evaluate to false. So therefore, the next instruction to be executed will not be here, but there. So therefore, the PC will be updated to point to here, right? So which means that n is greater than 0. So now these instructions will be executed when the parent process is executing in the CPU. Assume after a while a context switch occurs. The kernel decides that, okay, this parent has run long enough in the CPU, let's give the CPU to the other process, which is the child process. So now this state will be saved here, okay? So that means you will just copy those again back to the parent's PCB. You do a context switch now. So that means you are actually, after you do it, copy, that means you are pointing to that place in the PCB, right? And then you load this PCB, some values from there into the CPU. That means now the CPU PC register will point where this value was pointing, right? So that means to that point in the memory, which contains the next instruction of the new program to be run in the memory, okay? So now that program will run. So this is the child process. Now that program will run, and that's a condition, okay? We have a check here. So n will be checked against 0. Is it equal? Yes, it is equal. So we will just jump to this block of the statement and execute the codes there. So in this way, you see that the child and parent is executing two different portions of the same program. All right, and this is what's happening briefly inside the system when two processes are running, when one is created by the other one and so on. Any questions here? Okay, of course, some details are very different, maybe a little bit different, but the basic idea is the same, okay? So how you push the values y and 0 into the stack and so on is maybe implementation dependent, but the basic idea is the same. So let's have a break, 10 minutes, and then we will continue.